In this video, we will look at combustion analysis. So combustion analysis is the big sister of empirical formula type questions. Combustion analysis questions tend to be a little bit more challenging, but very similar procedure. There's more than one way to do it. I'm going to recommend that you do it the way I show you, but you'll find other ways to do it. It really doesn't matter which way you pick. I would pick one method rather than dart in and out of different methods and practice the same method over and over again to get some muscle memory. Okay, so we have a question. A 4.24 milligram sample containing only carbon, hydrogen, and oxygen is burned. The reaction produces 6.21 milligram of carbon dioxide and 2.54 milligram of water. The molar mass of the compound is approximately 180 grams per mole. What is the molecular formula? Okay, so let's go ahead and create some space and let's answer the question. These questions typically take about 5 or 6 minutes to answer if you know what you're doing. They're definitely not a 2-minute question. Okay, so we have combustion, so we know that there's carbon, hydrogen, and oxygen only in some ratio, and the whole point is we don't know what that ratio is. So let's call it X, Y, and Z. It's a combustion reaction, so we know that this sample is going to be the fuel. We add gaseous oxygen, and we know based on something that contains carbon and hydrogen only, it's going to produce CO2 and water. We're not going to worry about balancing it. In fact, we can't balance it, can we? Because we don't know what X, Y, and Z are. But that's the gist of what's going to happen. And we have to, identical to the empirical formula questions that are on a previous video. So I would definitely watch that video first. You need to get the percentage of each chemical, and then we'll eventually convert the percentage to gram and then finally moles. Okay, so the strategy is let the percent of carbon equal the grams of carbon divided by the grams of the sample as a percentage. Okay, so let's do that. So we're going to have a dimensional analysis calculation here. Okay, and we're going to get percent carbon as the output. So let's retrofit it. So we're going to end up with 100%. Okay, and then my numerator is going to be grams of carbon. So let's go ahead and put grams of carbon. I know from the periodic table 12.01 grams of carbon by definition is a mole of carbon. So you'll need a periodic table with you. I know that a mole of carbon is equal to 1 mole of CO2 because one of these contains just 1 carbon, so it's a 1-to-1 mole ratio. So mole of CO2 goes up here, mole of CO2. I know by definition a mole of CO2 is the weight of CO2 in gram. So I add 1 carbon and 2 oxygens, add them all together, that's 44.01 grams of CO2. I'm just giving all the weights to 2 decimals. There are some people that are adamant that you need to give more than 2 decimals. I was always taught that 2 is fine unless you're doing something that requires more analytical precision. So if this is a general class, I think it's fine. If your instructor tells you otherwise, then obviously follow those procedures that you're given. Okay, so we've got gram of CO2 gets promoted. Due to a lack of space, I'm just going to do the metric conversion in my head. So to go from gram to milligram, or rather to go from the input, which was milligram in the question. So if we remind each other here, Yeah, we're given milligram, aren't we? So to go from milligram to gram, we would have to divide by 1,000. So if I take my 621, well, 6.21 milligram, that would be 6.21 by 10 to the negative 3 gram. That's my input. So I've got my numerator. All of that was just to get my numerator in grams of carbon. My denominator now has to be gram of sample. So again, I have to divide by 1,000. So 4.24 by 10 to the negative 3 grams of sample. Okay, so the only units that survive are my gram of sample as a denominator, my gram of carbon as a numerator, and a percentage. All of the units cancel. I am good to 3 sig figs. So although I don't want to round my value yet, I want to keep a track of the sig figs. So I run this through my calculator and I get 39.9. They're my sig figs. My dash represents where my insignificant digits begin. And I give my 2 non-significant digits so that I can eventually round correctly later on. Okay, so 39, almost 40% carbon. Okay, moving on, we're going to do something similar with hydrogen. So we're going to say that the percent hydrogen, actually let's do hydrogen in a different color, just because we can. For no other scientifically valid reason other than we can. Okay, so percent hydrogen, let's say, is the grams of hydrogen over the gram of sample as a percentage. Okay, so let's execute that plan. And we're going to get percent hydrogen. So we'll start with a percentage. We're going to retrofit this backwards. I know from the periodic table that 1.01 gram of hydrogen, well, by definition, that's a mole of hydrogen, isn't it? Put mole of hydrogen up here. I know that there's 2 moles of hydrogen in 1 mole of H2O because there's 2 H's in 1 H2O. So we have mole of H2O up here and we can cancel. I know that there's 1 mole of H2O has a mass of 18.02 grams of H2O. So we just add the 1 oxygen and the 2 hydrogens, add them all together. Okay, again, I've got to convert my milligram input to grams, so I divide by 1,000. So 2.54 by 10 to the negative 3, that's just my input for my mass of water. And my sample now, my sample is 4.24 by 10 to the negative 3 gram sample. So exactly the same sample as before. Good to 3 sig figs, so let's run it through. And that gives me 6.71. There's my boundary with the sig figs. And 5 and 2 are my 2 additional insignificant figures that I propagate so that I don't round as I go. Okay, so I've done all I can. I've got the percentage carbon, the percentage hydrogen. There's a problem with the percentage oxygen, and this is what makes combustion analysis the big sister of empirical formula type questions. I don't know how much oxygen I have because I have 2 sources, right? I've got the oxygen that I want that's originally in the sample, but I'm also pulling in gaseous oxygen from the environment, from the surrounding, and both of these sources go into the final product. So I don't know what fraction came from the sample, and I don't know what fraction came from the oxygen that was needed to combust. So that creates the extra problem. But I do know that the percent oxygen is going to be everything minus the stuff I know that it's not oxygen. So 100% of the sample minus the percent carbon minus the percent hydrogen. So that's what I do know, and that's how I'm going to calculate the oxygen. So now, it's not just 100 to 1 sig fig. If all of my percentages have been 2 decimal, oh, actually this one's been 1 decimal, right? When I subtract, I propagate least decimal, so I want to write, to go at least, I definitely don't want 100 to limit what I do know, so I'm going to write 100.0 to preserve 1 decimal. All right, so this is 100.0% minus the percent of carbon, which we said was 39.968, and then minus the percent hydrogen, which we calculated to be 6.7152. So that was the percent carbon, that was the percent hydrogen. So that equals 53.316% oxygen. Again, I'm subtracting now, so I propagate least decimals. I had 1 decimal in my known, so I made sure I had 1 decimal here so as not to limit the least decimals in my known. I had 2 here, but 1 is less than 2, so I know I'm good for 1 decimal, and I propagate 2 extra digits so I don't round prematurely. Okay, that's the extra step that you don't get from a regular empirical formula question. So we're about halfway through. So let's continue onwards and upwards. I am going to go back to, well, let's stick in blue. Let's stick in blue just because we have it. So the strategy now is, now we've got percentages. We're going to go back to gram, and then eventually to mole, and then that's how, essentially the same strategy with empirical formulas. Okay, so let's do it. Carbon, we convert that percentage to a mass, so 39.968, it's now grams of carbon. And I know that 1 mole of carbon, by definition, is 12.01 grams of carbon. And that equals 3.3278 moles of carbon. Okay, let's do the same for hydrogen. Hydrogen, I've got my percentage, which is now a grammage, 6.7152 grams of hydrogen. And I know that 1 mole of hydrogen is 1.01 grams of hydrogen. Cancel the units. And that gives me 6.64. The 8 and the 7 are not significant, but I propagate them. Moles of hydrogen. And I can do the same lastly for oxygen. So oxygen, I have my 53.316 grams of oxygen. I know that 1 mole of oxygen, 16 grams of oxygen. And I know that this is 3.33 and 22 moles of oxygen. Okay, so everything is like empirical formulas now. But let's show our workings like good chemists. So far I know I've got C 3.3278, H 6.6487, O 3.3322. And what I have to do now, let's change the pen just to, I don't know, just to do it. We have to divide through by the smallest number, which in this case is the first number, 3.3278. Divide throughout by 3.3278. Correct your typo as you go. I just found a typo, which is wonderful. Glad I caught it. 3278. 3.3278. All right. That goes into itself once, that goes into that once, and that goes into that twice. So this tells us we have, let's go back to blue. This tells us we have CH2O as our empirical formula. Right? It's the 1 here, the 2 here, and the 1 here. We know it's empirical because we followed the procedure. We also can vet that it's empirical because that 1 to 2 to 1 ratio, there's no way to reduce that down any further and maintain whole integer numbers. Okay, let's calculate the formula weight of that. So the formula weight of our empirical formula is carbon, which is 12.01. And then we've got 2 hydrogens, which is 2 lots of 1.01. And then we've got 1 oxygen, which is 16. And they have units, all have units of gram per mole. So that equals 30.03 grams per mole. So that's our formula weight. Remember from our empirical formula video that that's the brick. We now need, ultimately we need to find the wall, which is the molecular formula. So remember that n multiples of empirical formula is equal to the molecular formula, whether it be number of atoms or the mass of the atoms. So this implies we need to quantify the integer n, right? So n is the molecular formula divided by the empirical formula. And here we're talking about the masses. Well, the question gives us the molecular weight. It says it's approximately 180 grams per mole. And we've just calculated through honest blood, sweat, and tears that the weight of the empirical formula is 30.03 grams per mole. So those units are going to cancel them. N is a unitless integer. The calculator is going to return a value of 5.99, which clearly, if we have to report a whole integer, just means that it's 6. So finally, all this work is going to pay off. So we know that we've got to scale our empirical formula by 6. And that's going to give us C6H12O6 as our molecular formula, which, for what it's worth, is glucose. Okay, so as you can see, it took, I didn't write that small, but it definitely takes more than a few lines to do a combustion analysis type question. And on an exam, when you're not having to go slow to explain it on a video, you definitely want to leave yourself a good, I would say 8 minutes to do it comfortably and check your work. So that is a short video on combustion analysis, the big sister of empirical formula type questions.